In the last section, we found the correlation coefficient, which basically told us how well the X and Y data, how well the paired data matched up. What kind of relationship did it have, if any? Here, we're going to find what's called the regression line, or the best fit line that goes through the data. So it's a straight line that best fits a scatter plot of the data. The basic form of this is y hat equals b naught plus b1x. You might also find this as the b naught is just called b, and the b1 is m for the slope. So this is really just a linear equation for a straight line, y equals mx plus b. It just depends on the textbook that you're looking at. X is the independent variable, or the predictor variable. Y hat is the dependent one. It's the response variable. It's the one, essentially you're trying to make a prediction about an unknown point, an unknown value of x. B naught, again, is the y-intercept, sometimes labeled b, and b1 is the slope of the regression line. Now, there are two formulas for each one, depending on the information that you have available. So b1 can be found if you know the correlation coefficient, and then these are the standard deviations in both y and x. The b naught you can find from rearranging the equation, and this is the mean of y, mean of x, and b1 here that we just found, which could also look like this: the sum of the y's over n, that's your mean of y. The sum of the x's over n, that's your mean of x. And again, like I said, depending on the information you have, there is a secondary way of doing it. So for instance, n number of pairs of data times the sum of the xy's minus the sum of the x's times the sum of the y's over n times the sum of the x squareds minus the sum of the x's squared. And then for your b naught, similar, sum of y times sum of x squared, subtract sum of x times sum of xy, all over n times sum of x squared minus sum of the x's squared. So their denominators are the same, but they have slightly different numerators. Now, requirements, these are simple random sample of paired data. Visual examination of the scatter plot shows that the points approximate a straight line pattern. So, basically you can do the math, but if the lines themselves don't kind of line up in something approaching a straight line, approximately, it doesn't have to be right on a straight line, but approximately, then, your equation isn't really going to mean much. Outliers are removed if they are known to be errors. However, if you don't know them to be an error, then generally it's a good idea to do your regression line both with and without the outliers to see what kind of difference that it does make. Now, part of the point of doing this is to make predictions on values that you don't have. The regression equation is a good model if the regression line graphed in the scatter plot fits the data well. In other words, none of the data points are really very far from your regression line. The R indicates that there is a linear correlation, so it's got to be near 1 or near -1. The prediction is not much beyond the scope of the available data. So in other words, if the regression equation is a good model and we substitute a given value of x, it does not have to be an x that's actually in the data set. Then when we get a value of y, it should fit. But you want to make sure that the x value you have is within the range of values that you've got going. So in other words, this tends to be used more for interpolation than extrapolation. Marginal change, that just means, how much does one variable change with respect to the other one changing by 1 unit. Remember that the slope, b1, in the regression equation is the marginal change in y when x is changed by 1 unit. An outlier is a point that's far away from the other data points. And then influential points, points that strongly affect the graph of a regression line. If there is a significant change in the graph of the regression line between including a particular data point and not including the data point is considered influential. Now, finally, we can do what are called residuals. A residual is the difference between the observed sample value of y, in other words, what you already had, versus the predicted value of y from the regression equation. And so basically it's just the difference between the two. A straight line satisfies the least squares property if the sum of the squares of the residuals is a minimum. In other words, it's not very big, the smallest sum possible. A residual plot is a scatter plot of the x and y values after each y value has been replaced with its residual. So, in other words, instead of your plot being x and y, your plot is going to be x and the difference between what were your y values and what were your predicted y values, that difference. The residual plot should not have any obvious pattern, not even a straight line pattern. The lack of a pattern confirms that a scatter plot of the sample data has a straight line pattern instead of some other pattern. Remember that data can have other kinds of patterns besides straight line. It could be something that's more quadratic, like a parabola. It could be something that's exponential. Those are still patterns. They're just not straight line patterns. The residual plot should not become wider or narrower as you move from left to right. This confirms the y values have the same standard deviation for different fixed values of x. For that matter, all your residuals should not end up below or above the line. There should be, kind of equal distance about the line, since you're supposed to end up with the smallest sum of those residuals possible. So here are some example residual plots. Here, we've got some scattered on the bottom, some scattered on the top. Clearly don't look like a straight line or any other pattern, so that would suggest that the regression equation is a good model. On the other hand, this one, there is clearly a pattern to our data points, and so that would suggest that the regression equation is not a good model. And then finally, here is one in which they all started together and then they started getting further and further apart. Again, that would suggest that that is not a good regression equation. Alright, so what we're going to do now is try to find our regression equation for a couple of examples. Most of this stuff has already been worked out for you, but follow along. Now, first off, what we're looking at here, and this was an actual study done. This is the paired data are the percent increase in the consumption of chocolate by a country and the percent increase in the number of Nobel laureates that that country has. So the X's are the chocolate consumption and the Y are the Nobel laureates. All of this stuff is done in Excel. So now we've taken our X's and squared them for X squared, our Y's and squared them for Y squareds. X times Y gives us the XY column. Now, once we have those, we can do things like sum them up. So we can have the sum of the x's, the sum of the y's, sum of the x squared, sum of the y squareds, and sum of the xy's. Once we, of course, have our sum of x's and y's, we can find their mean and then find their standard deviation. And in a program in Excel, that would be just like taking an average, and this one, literally, you just say standard deviation of, and then you highlight the whole column. So now we have our means and standard deviations. That allows us to find the z-scores for our x and y values, the zx for the z-score for the x's, and the z-score for the y's. Remember that z-scores are just x subtract the mean divided by the standard deviation. And then we can also then, now that we have zx and zy, we can multiply those. And you'll see why we want to do that later on, but then we can sum those up as well. So basically let Excel do all of that work. Now that we have all those values, I can go ahead and use my initial formulas to figure out the slope of that line and its y-intercept. So R, here was our R, 0.80061. I didn't recalculate it here. We had it calculated back in section 9.1. But so there's the same one we had, times the sy over the sx, and we get that our b1 is 2.493. Our b0, the b-intercept, or the y-intercept, mean of the y, subtract b1, times the mean of the x's. Go ahead and plug those things in, and we have negative 3.367. Now, that's one way to do it, just so that you can see, depending on what information you have, we can do it the other way as well. So these are the more expanded equations, but with my Excel I have the sum of the x's, the sum of the xy's, x squareds, y squareds, x times y's. Since I have all those, I can use those now in my equation, and just so that you can see that they do in fact come out just what they did before. And so then my equation, y equals b0 plus b1x, and there is my regression equation. And it does not matter if you put the 2.493x first and then the negative 3.367 second. So whether you do it this way or this way is fine. And I should mention, we used that data set up above when we were in section 9.1 to find R, the coefficient of correlation. Now that I have an equation, okay, it's a good idea to make a plot of it. So here's my scatter plot with the line actually plotted in the scatter plot, so you can visually see, does it kind of fit the data or not? There are clearly some points, these would be kind of outliers, but there's a lot of the data that's not too far off the line. In terms of a predictive value, let's just say x equals 10, plug it in, 2.493 times 10 would be 24.93. That gives us a predictive value of 21.53, so we would say then an increase in 10 kilograms of chocolate per capita predicts a rate of 21.5 Nobel laureates per 10 million people. That also gives you some ideas about what the units were for our numbers. Visual inspection of the line shows that it fits the data fairly well, but there are some points not very close to the line. Predicted values should only be for data values that don't go far beyond the scope of the data. Since the regression equation appears to be a good model, it fits the data well, and there was evidence for a linear correlation. Remember that was 0.8. Then we can use the model to make predictions, such as the one we made here with 10. 10 would have fallen right in here. So it's within our data set. If we started getting out here, clearly with these points that are not so close, we would have less confidence that we might have a good value for our prediction. Now, let's look at a residual plot. So what I've done here is, here's x, here's y, and now here are the y hat values we would get if we took in the x and plugged it into this equation. Okay, so sometimes if the dot falls right on the line, they should be really close to each other. 6.1, 6.3. Let's see. Some of them are pretty, 1.9, 1.6. So some of them are pretty close, but some of them are not so close. And so we can do our residuals. So this is y minus y hat. The y value that we got in the original data set, subtract the y value that we got from our equation, our best line fit. And then now this is what this plot is. This plot is showing you the residuals versus the value of x. So x is still the horizontal axis, but now we have the residuals on the y. Some of them, of course, are too high, positive values, and some of them are too low, negative values. That's all the negative means. It's a situation in which the original value was below the predicted value, so we got a negative difference. Not sure you can really say that there's any real pattern here. I mean, there's clearly an outlier point type there, maybe there. It doesn't clearly get bigger as we go across, and again, there's no real pattern. We have a number of them above and a number of them below, again indicating a pretty good fit for our line and a pretty good correlation between the consumption of chocolate and the number of Nobel laureates. All right, so let us look at a second situation, just so you can go through some of the process once again to find the line. So we have a smaller data set here. This is find the regression line for the level of GDP, the gross domestic product, so sort of the economic health of the country versus the CO2 emissions of the country. And then use that regression equation to predict the CO2 emissions level for a GDP of 2.6. And, quick glance at my X values, I don't actually have any of them that say 2.6, but it is within the range of values. So, similar to what we did in the other data set, go ahead and find our sums, sum of the x's, sum of the y's, sum of the x squareds, y squareds, x y's. These we could use, or these, to find the residual. Note this has, the correlation coefficient. The correlation coefficient is higher in this particular data set, 0.87. The other one was 0.8. And then we have our means and our standard deviations. So I can find B1 and B0. And again, B1 is the slope and B0 is the y-intercept. So as I said, in some texts, B1 is called M for slope. So don't let that bother you. So please note, I get pretty close, not exactly the same between the two methods. Probably the difference between those is just a matter of rounding. How many digits did you plug in when you did your secondary calculation? Likely, if you had carried all the possible digits that the program could use, these would have come out very, very close together, at least for 3 or 4 decimal places. So then I got my answer. My regression line is y hat equals 56.036 plus 199.535 times x. Do you need 3 decimal places all the time? Not necessarily. It's going to, on a homework problem, it's just going to depend on what they want. It probably won't change your answer significantly if we had only gone to the tens place. Now we're going to do our prediction. We're going to put in 2.6 for x, and we get a 574.827. So that basically says if we had a country whose GDP was 2.6 trillion, that the CO2 emissions would be 574.82. Probably parts per million, but I'm not positive. So that is section to basically find the line of best fit through the data.